Hello everyone. In this lecture, I'm going to solve one example of the viscosity in driving and determining shearing stress and based on the viscosity in a Newtonian fluid. And after that, we are going to start, this will finish this chapter 1 of the book, and then we are going to go to the second chapter, which is about fluid statics. And we are gonna start with some introductory remarks and definitions about pressure, Pascal law, and some definitions about statics, fluid statics. Okay, so let's get started. So I'm gonna solve an example. The velocity distribution for the flow of a Newtonian fluid between two fixed plates, similar to what we had before. It's not similar to what we had before, because what we had here in the definition of the viscosity, we only had one fixed plate, right? And the other one was moving, right? So it's a little bit different than that. Now we have two fixed plates, and then we have fluid that is moving within these two fixed plates. Between two fixed plates is given by the equation U equals to 3 capital U over 2 1 minus y over h square, where capital U is mean flow or average flow velocity. And y and h, I'm gonna draw the shape so you better understand what it is. So this is the first plate. This is the second plate. And then we have some fluid that is moving within these two plates. Okay. And so these are fixed plates. Okay. So the velocity profile is distributed based on this equation, right? This equation that you see here. So if I want to draw it, it will have a shape like this. So let me just draw it here. the velocity profile. We call this velocity profile. It just shows the velocity at each point. Okay. So it's gonna be something like this. This shows the velocity at each point. And this is a parabola, right? Based on the formula that we have here. It should be a parabola, a parabolic form. And so the y coordinate starts from the center. So this is y. And this distance is h from each side. So when y equals to h, meaning when we are here at this point, then this is going to be 1. So the whole thing is going to be 0, because 1 minus 1 is 0, so the whole thing is going to be 0. And the velocity here is also 0, as you can see it. So this shape is consistent with that. And when y is 0, we have the maximum velocity, which you can see it here, right? This is the maximum velocity. Okay. So then the problem states that this mean velocity or average velocity, which is the average velocity of the flow, and we will go through more details later, it is something like here. It's going to be the average. If you average this profile in y, you are going to get something like this, right? So this average velocity or mean flow is 2 meters per second. H, this distance here, is 3 centimeters. And mu, or viscosity of the fluid, is 8 times 10 to minus 4 Pascal, or Newton per meter square. Okay, so now the question asks, determine A, the shearing stress acting on the bottom wall and B, the shearing stress on a plane parallel to the walls and passing through the center line. Okay, so we have to determine the shearing stress, and these are fixed plates, so I'm just gonna show it like this. Both of them are fixed plates, so they are not moving. It's just a fluid within them that moves. Okay, so now let's see what is the answer of this question. So as you see, the question asked for the shearing stress tau. So the question asks for the shearing stress tau, right? So if you remember from here, from previous lectures, tau, or shearing stress, is in a fluid is defined as, and we showed it as mu, which is concept of proportionality or absolute viscosity, times du over dy, where u is the velocity of the fluid, right? So the gradient of the velocity with respect to y. So tau is going to be mu du over dy. Okay. So now I just I have the formula for u. I have mu, I have u, capital U, and I have h. And the only dependent variable here is, independent variable is y, right? So I can take the derivative of this function u with respect to y. What I'm gonna get is this. So this is gonna be tau equals to mu times 3 capital U over 2 times the derivative of this function with respect to y. So this is going to be just 0, right? We don't have any y here. And this one is going to be what? Is going to be 2y over h squared, right? This is from your calculus. So we are going to have minus 2y over h squared. These are all constants, and in any derivative, as you know, you can keep the constants and then just differentiate with respect to the independent variable. So for example, here you're gonna have two terms. These are just reminders. 3u over 2 minus 3u over 2 times h squared times y squared, right? So the derivative of this one with respect to y is 0, and the derivative of this one with respect to y is going to be, we keep the constant 3u over h squared, 2h squared, times the derivative of y squared, which is going to be 2y. And that is what we have here. If you look at it and compare this, these are the same things. Okay. So this is going to be what? These two are going to cancel out. So I'm going to have minus mu 3u y over h squared. Okay. So this is the general formula for tau, for shearing stress that the question asks. But in A, the question asks, find this one along the bottom wall. So along the bottom wall, which is going to be here, right? Y is what? Y is minus h, right? Based on the definition and the coordinates that we have here, y is, and the bottom wall is going to be minus h. So we just substitute. We just substitute to get the value of the shearing stress at the bottom wall. So tau bottom wall is gonna be, we have minus h, so we are gonna have minus mu 3u, and instead of y I have to put minus h, right? Because y is minus h over h square. So I'm gonna have mu, these two are gonna cancel out, I'm gonna have h here, so it's gonna be mu 3u over, 3u over h with a plus sign. So I'm just now gonna substitute the numbers that I have here. Mu is what? Is 8 times 10 to the minus 4 Newton per or Pascal. So I have 8 times 10 to the minus 4 Newton per meter square. It is Pascal second. I forgot to add. So this is Pascal second. And then I have a second here, which is time. Then I have 3 times u. U is what? Is 2 meters per second. So I'm just going to write it 2 meters per second over h. What is h? H is 3 centimeters. So it's 3 times 10 to the minus 2 meters. Correct? Okay. So first, these meters are all going to cancel out. These 2 meters are going to cancel out, right? And then I have a second here. So these 2 seconds are also going to cancel out. These are just the units. You can also do it for the units. And so the unit of this is going to be Newton per meter square, which is correct, which is stress, and that is what I wanted. And then these 2, 3 are going to also cancel out. And finally, these 10 to the minus 2 is going to cancel out, and this one is going to be 10 to the minus 2. And so I am left with what? And just so you know, Pascal is also Newton per meter square for those people who might be confused. 1 Pascal is Newton per meter square. So that's why here I wrote, instead of Pascal second, I wrote Newton per meter square a second. So this is going to be 2 times 10 to the minus 2 times 8. So it's going to be 16 times 10 to the minus 2. So it's going to be 0.16 Newton per meter square. In the direction is a positive number, so the stress, the shear stress is in the direction of the flow, right? So in the direction of the flow. So this is going to be the shear stress at the bottom wall. So this is going to be the shear stress here. We have the shear stress here. It's around 16.16 Newton per meter square. Okay. And then B, we have along the midplane. This is what the problem wants from us. The shearing stress on the plane parallel to the walls and passing through the center line. What is the center line? Center line is here. So along the midplane y, what would be the value of y here along the midplane? We just start from there, right? This is a definition of y, where we start from there, so y is going to be 0. So when y is 0, and this is the formula that I have, you can guess what is going to be the tau. So tau of midplane is going to be what? Is mu 3u times 0, right? Over h squared. So it's just going to be 0. 0 Newton per meter square. So the shearing stress in the center line is going to be 0 and is going to be 0.16 Newton per meter square at the bottom wall. So if I want to plot this formula here, 3uy over h squared, we are going to get something like this. So let me plot it. So this is y. I kind of think about it that I have rotated it, right? So what I'm plotting now is something like this. And this is tau. Okay. So we have 3 points. So the formula is like this. Let me just first write the formula. So tau is minus mu, let's say 3 mu u over h squared. So minus 3 mu u over h squared. All of these are constant in this problem. Times y, right? So it's just a straight line, right? It's a straight line. And if this is tau and this is y, it's going to be a straight line. It's like f x equals to a times x, right? So this is going to be a straight line with a negative slope, right? Because we have a negative slope here. So if you plot it, we are going to get something like this. For the stress. Trying to be symmetric. Okay. So along the center line, y is what? Is 0. So this is y, which is 0. And our tau, or shearing stress, is going to be also 0. When y is minus 3, this is y, right? Then the shearing stress is going to be 0.16. And this is what we found. Tau at minus 3, which is minus h, and this is 3 based on centimeter, so this is the unit centimeter, and tau, the unit is Newton per meter square. And when y is 3, right, 3 centimeter, then y is 3 centimeter, then tau is going to be minus 0.16 Newton per meter square. So we have just a different direction. of the shearing stress, right? So this is how this looks like, this shearing stress that is applied to the fluid on a plane, on the planes that are parallel to the fluid, right? So this was just an example of how you can use this. This is a very important formula that you need to know, and how you can apply this to find the shearing stress in a fluid, right? So typically in fluids, we have these velocity profiles, okay? For example, for pipe flows or different types of or channel flows, we can get these either from experiments, like we do some experiments and then we find how this velocity profile looks like by putting some, for example, some anemometers. If it's the air, then you can get the velocity profile and how it looks like. Or from some theory, sometimes you can also, from theory for some simple shapes like pipe flows, we can get these formulas for laminar flows, of course, not for turbulence, and we will talk about their difference, what is the difference between laminar and turbulent flows. And once you have these formula for velocity, you can get the shearing stress for a Newtonian fluid if you have the viscosity of that fluid. It's important to note this formula is only valid for Newtonian fluids. And by Newtonian fluids means for fluids which are the focus of our course and in which the shearing stress is linearly related to the rate of shearing strain, right? So for these kind of flows, any flow where we have this linear relationship. And for those non-Newtonian fluids, they are not the focus of our course. And they are mostly, as I said before, studied in like material science, where for specific kind of materials like toothpaste or some plastics or polymers, these kind of things, where there is a nonlinear relationship between tau and shearing strain. But for this course, because most of civil engineering is focused on water and sometimes on air, both of these fluids are Newtonian, and so we can use this formula, which is tau equals to mu du over dy. So in this example, we examined that we had this given velocity profile, which was 3u over 2 times 1 minus y over h squared. These properties of the flow were given to us, which was the mean flow velocity, u, 2 meters per second. We had the h, which was 3 centimeter, and also the mu or viscosity of the fluid was also given, which is Pascal second. And the problem asked to determine the shearing stress acting on the bottom wall, which is here, and also on the middle wall or in the midplane. What is the shearing stress? And based on this formula, what we had to do, we had to just take a derivative of u with respect to y, and we took that derivative, and this was the result. And then after that, it was just some substitution, right? So we just plugged all the numbers that we had, like y along the bottom wall, y is minus h. So we just plugged that in, and we got 6.16 Newton per meter square. And along the midplane, y is going to be 0, so this tau is going to be 0. And so we got tau in the midplane was 0 Newton per meter square. And if you plug this and plot this tau here, tau versus y, you're gonna get this figure here. So it shows that this is gonna be the midplane. In the midplane, the tau is gonna be 0. This is the bottom wall. In the bottom wall, it is 0.16, and along the top wall, this is gonna be 3. It's going to be minus 0.16 Newton per meter square. So it's important to note here in the middle plane, it's interesting that we will have no shearing stress acting on this fluid. In the middle plane, there is no shearing stress. And the shearing stresses are caused by these walls, right? By these fixed planes. That's why, because these planes do not allow the fluid to move, right? So because of the friction, the high friction here, because they are not moving, so the fluid has to adjust itself with these planes, right? And so because it has to adjust itself with these planes, it will create some friction, and therefore it will create some stress, some shearing stress that the fluid has to tolerate, right? So, and it cannot have a free movement because of these fixed plates. And so that's why we have the maximum shearing stress along these planes, along these fixed plates, right? And we have the lowest one in the middle because the lowest one does not feel any friction from the sides, and the shearing stress there is gonna be 0 based on this formula. But of course, for more complex problems where we have a very big velocity, very complex velocity, and it's gonna be turbulent, and these are the things we are gonna study in the second half of the semester. We have turbulent flow, so the flow is not as smooth as this all the time. In those kind of problems, because the flow is gonna moving like this, is not necessarily moving straight, then we are gonna have also stress in the middle of the of a plane. But for kind of these low velocity, like 2 meters per second or even less than that, pipes or these plates, 2 fixed plates, we will not have such scenarios. So the shearing stress in the middle of these 2 fixed plates is gonna be 0. Okay, so this is the end of first chapter. This chapter, I just wanted to give you some introductory remarks about the fluid, how these problems in fluids look like. Talk about viscosity, different type of fluids, which are Newtonian and non-Newtonian fluids. And from the next chapter, we are going to start the real fluids, which is fluid statics. So we will talk about the pressure forces in a static environment where the fluids are at steady state, how we can gauge and write the pressure formulas. And after that, we're going to introduce Bernoulli equations, and then after that you're going to go through dynamics, which is going to be more complicated, where we also have acceleration of the fluid itself, which also acts on different objects. And so this is how we are going to move forward in this semester.